तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So, last class we were discussing the emitter function logic, which is a variation of the emitter couple logic, and we have seen that the functionality is tremendously over the emitter couple logic, in the sense that with the same power dissipation you can realize logic circuits of much greater complexity. Okay. So, effectively you are reducing the power dissipation. Okay. So, we shall continue our discussion on the emitter function logic, and we will take up again the basic circuit of the emitter function logic, which is something like this. You have multi-emitter transistor, this is the output side, and then you have the emitter couple structure here, the current source, this is minus VEE, this is ground, and here this is VR, then you have a level shifting arrangement. So, this is VR minus V on, and you have the inputs, this is A, capital A, and this is small a1 and small a2. The capital A is actually called the control input. Okay, these inputs here at the base of this transistor is called the control input. Okay, whereas these inputs small a1 and a2 are called the direct inputs. Okay, that is the name that is, and the configuration, the circuit configuration is like this. So, you have the control input here, you have the OR gates, okay, you have A1, A2 and like this. So, F is equal to A1 plus A bar, A2 plus A, which can be written as A1A plus A2A bar. All right. So, we have seen this, and so this is the logic we achieve, and we have also seen that we can increase the complexity by, instead of having an inverter structure here, you can have a NOR structure. That is, if you have more transistors in parallel, okay, that is more number of control inputs, okay, you can increase the complexity that way. All right. Now, let us see, we will just take up a few examples of circuits. One is the exclusive OR, which I think we have already discussed last class. That is, if A1 input is taken as B bar and A2 input is taken as B, okay, then you get the F as A B bar plus A bar B, which is the exclusive OR gate. Okay. So, you can realize the exclusive OR gate by providing B bar at the A1 input here and B at the A input. Okay. The next thing which we can take up is the D flip flop, okay, which is a very important circuit. When you go for any synchronous logic circuits, you have to have flip flop, okay, and so let us see how you can realize a D flip flop. Okay. What is the function of a D flip flop? The D flip flop function is that when the clock is high, whatever is the value at D should be passed on to the output, and when the clock is low, whatever was the previous output should be retained. Okay. So, we can write like this: Qn is equal to D into clock plus Qn minus 1 clock bar. That is, when the clock is high, okay, that is clock is 1, clock bar is obviously 0. Okay. So, when clock is high, Qn is equal to D. Whatever is the D input is the same as Qn, and when clock is low, that is okay, this clock is 0, clock bar is high, then whatever is the Qn minus 1 is the same, the Qn is equal to Qn minus 1, that the previous value of the output is passed on, previous output is retained, basically Qn minus 1 is equal to Qn. Okay. Now, when you compare this with the standard function which is realized in a D flip flop, okay, you see it is quite similar. Okay. So, what you have to do is, the clock input must come as the control input here. Okay. A should become the clock, and in one case A1, the small a1, it can be D, okay, and the other one should be Qn minus 1. All right. So, if you do that, you will realize a D flip flop. Okay. So, I shall just draw the circuit. Okay. I can just modify this circuit here maybe, okay, on the blackboard. Okay. This A, we will come back to this circuit. So, here instead of A you have clock, okay, and then what about the A1, small a1 is going to be D, isn't it? When clock is high, Qn is D, all right, and when clock is low, that is the output is equal to Qn bar, the previous value of Qn. So, here for small a2 you must feed the previous value of Qn. So, what you do, you take the one output here, okay, and it must be fed back here, all right. So, just have to take, there is always a feedback in a flip flop, okay. So, this is the feedback, okay. So, the output comes from here, okay, whatever is the previous output is fed here, okay. So, when clock is low, then the next output is going to be the same as the previous output, okay. So, this completes the D flip flop, all right. So, you see that this is the circuit of a D flip flop, and again the power dissipation is corresponds to that of a single gate, all right. You have a single current source here, okay, and of course, you can realize a master slave D flip flop, okay. How do you do that? You have to have a similar gate, all right. I will just draw it because to give completeness, okay. So, you have a similar gate, okay. Just drawing a similar gate. So, this minus VEE is drawn here, okay. This is VR, and again you have this, okay. Now, here is the output. So, you have a similar gate means, but the only difference being, what is the only difference? That the clock is going to be inverted, okay. So, what you do is, all right. So, this VR for this first gate. So, basically the clock, I think what I should have done, what I should do now is, I think I will remove this, okay. This clock, this VR should be fed here, okay, and the clock, okay, should come here, the same clock. So, basically I have inverted the position of the clock and VR. So, this VR comes here, okay, same, and the clock. So, now here you have the D input, okay, as in the previous case. So, this goes the D input, okay, and here you have so this is the circuit, all right. Sorry, this one. So, this completes the circuit for a master slave D flip flop, okay, all right. So, you have two stages, and the difference between the two stages is that only in one the second stage the position of the clock and the reference voltage is reversed, Okay, right. So, this is the circuit of a master slave D flip flop. So, you see that again what is important here is that we have achieved it with a lot of saving in power supply, in power dissipation. Okay. Now, after this only one issue which we have not really taken up is that we have to see whether this particular circuit satisfies the voltage compatibility requirement. Okay, that is, what is the voltages, what is the reference voltage. So, we have seen for ECL gate that reference voltage must be equal to minus 3/2 V on and so on and so forth. Okay. So, what is it going to be here and whether it satisfies the requirements. Okay. All right. So, now let us assume for example that I naught into R is equal to 0.8 volts. Okay, that is the current source value I naught into the resistance R is equal to 0.8 volts. Okay. So, the value, the voltage here at this node, okay, can either be 0 volts if this transistor is not conducting, or it can be minus 0.8 volts. Okay. So, here it can either be 0 or the voltage variation is 0 to we shall write 0 to minus 0.8 volts. Okay. This voltage variation at this particular node. Okay. Now, so what is the output voltage variation? What is the output voltage drop? So, if we assume that the VBE of this transistor is 0.8 volts. Okay. So, the output voltage varies from minus 0.8 to minus 1.6 volts, minus 0.8 volts to minus 1.6 volts. Okay. All right. Now, the VR of this circuit, okay, let us choose it to be minus 0.4 volts. Okay. All right. And so, VR minus V on is going to be how much? Again minus 1.2 volts. Okay. So, for the lower part of the stack, here, say here, let us draw, suppose I think we will take a different circuit. Okay. Let us have the normal configuration. So, here you have a diode drop and the resistance. So, this reference voltage is going to be minus 1.2 volts. Okay. All right. So, let us say that the output of the first stage is going to be fed, it can be fed either as input here as a control input, as a direct input, or as a control input. So, let us see if the voltage requirements are satisfied. So, when the output of a particular gate, so this is the gate 1 is fed as a direct input, okay, here, all right, what happens? Now, you have again an emitter coupled structure here. Okay. This transistor, that is the output transistor of gate 1, and this transistor form a emitter coupled structure. Okay. The emitters are shorted here, you see. Okay. And this input here is minus 0.4 volts, and the input at the base of this transistor is varying from 0 to minus 0.8 volts. Okay. So, what we are having is a variation of this VR plus minus 0.4 volts at the base here. Okay. So, if this voltage here you see is 0 volts, okay, what happens? This transistor is on and this transistor is off. Okay. So, that is what we have said. So, if the input is high, we have said already that if the input is high, then this transistor is off. Okay. So, between this there is perfect voltage compatibility. You can feed this output directly as a direct input here without any level shifting necessary, okay, because this voltage varies about the reference voltage here. Okay. And suppose you have another input and you feed it directly here. Okay. So, actually you must have a resistance connected here, sorry I did not write it, okay, at the base, all right. So, now suppose you feed it here directly at the base. Okay. Now, what happens? You see this voltage here is minus 1.2 volts. So, this again is an emitter coupled structure, this transistor and these two transistors. Okay. So, T1 and T2 they form an emitter coupled structure. The base of T1 is minus 1.2 volts, and what is at the base of T1? The variation is minus 0.8 to minus 1.6. So, if this is minus 0.8, T1 will be on. If it is minus 1.6, T2 will be on. Okay. So, again you see that there is perfect voltage compatibility. Okay. That is, what we want to say is that the output of an EFL gate from this emitter multi emitter transistor can be fed directly either as a direct input here, okay, or as a control input here without the need for any level shifting. Okay. There is no level shifting required, that you can feed it either to this state level or to this level, okay, because they are perfectly compatible. They form emitter coupled structures here, as one can see, or here one can see, where the input here at the base of one transistor swings about the reference voltage. Okay. And so, if this input is high, this T1 is on, if this input is low, T2 is off. Similarly, if here this emitter coupled structure, if this is high, that is 0 volts, then this one is on, which means automatically this one is off. Okay. And if this goes to minus 0.8, then this one is off and this one turns on. Okay. So, you see that there is no problem from the voltage compatibility point of view. Okay. So, EFL circuit does not require any level shifting, although you have a stacked structure as here. Okay. That is the important thing, because level shifting again would mean that you require additional circuitry. Okay. So, we have gone through this emitter function logic, which is again, I will repeat, a variation of the emitter coupled logic, and the advantage is greater functionality, and you can achieve more complicated functions with the same power dissipation. Okay. So, that is one of the circuits which have been proposed. In fact, this was proposed way back in early 70s. Okay. Then there has also been a lot of work going on even further, because the problem is ECL gate is a very high speed circuit, okay. It is in fact offers the highest speed, but it is still difficult to make large scale integration, okay, because it is still very much power intensive. Okay. There is a lot of power dissipation, and so you cannot make very large very highly dense circuits. And so, even with these concepts, it is still the power dissipation is high, and so people have tried to work out more advanced circuit concepts to reduce the power dissipation. Okay. The one aspect people have been working on is to reduce the power supply voltage. Okay. That is another advantage. See, if you reduce the power supply voltage, you automatically reduce power dissipation, and in today's world there is also been a drive to have lower and lower power dissipation, also because of the fact maybe you want a lot of handheld equipment which can operate with standard battery cells and so on and so forth. Maybe 1.5 volts people are talking of. Okay. All circuits should work with that voltage. Anyway, so there has been a drive to reduce the power supply voltage, okay, which automatically means you reduce the power dissipation. So, I shall take up one more variation of the ECL family, okay, which has been proposed very recently. In fact, okay, it was first published in 1997. So, and it in fact claims that it is the it provides the lowest power delay product, okay, if on in the among circuits working in the gigahertz range. Okay. So, I shall just slowly introduce that particular concept. Okay. So, I shall draw the circuit, in fact, which I had drawn last class, okay, that is the standard ECL D flip flop circuit, okay, and we shall see how one can actually go ahead and see the difference. Okay. So, this is the standard D flip flop circuit using stacked ECL gates. So, you have two emitter coupled sets of emitter coupled transistors, and here you have in the lower stack another emitter coupled structure, okay, and here you have a current source, okay, and these are the clock inputs, clock and clock bar, okay, and so here you have one is the D input, okay, and the other is the reference voltage VR. Okay. The clock, one of the inputs goes here and the other input goes here, clock bar. So, one you have clock and the other is clock bar. Here you have D and VR, reference voltage, okay, and here you have, say, this one going here, this one going here, and then these outputs again go to emitter followers, okay, and you have one more emitter follower here, okay. This is minus VEE supply voltage, and so this is D, so this is Q bar, okay, and so this you have is Q bar, this is Q, all right, and the Q bar input should come here and the Q input goes here, okay. So, this is the circuit which we have already discussed, all right, the D flip flop circuit, okay, here, yeah. So, now let us see what is the power supply requirement for this circuit. So, in this standard circuit, okay, the input voltage variation between, say, clock or any of the inputs, okay, it varies from minus VBE, all right, minus VBE, that is the high value here, okay, all right, and say suppose you have the voltage swing is, say, 500 millivolts. So, usually in high speed circuits the voltage swing will be limited, okay. So, it is not full V on, so it is 500 millivolts, okay. You know that the power delay product will depend on the logic swing. So, you limit it to, say, 500 millivolts. So, this is 500 millivolts. So, this the input voltage variation, input as well as the output voltage should vary from minus VBE to minus 500 millivolts, and the reference voltage, it is centered about that variation, that is VR will be in this case how much, minus VBE minus 250 millivolts, okay, all right. So, this VR is equal to minus VBE minus 250 millivolts, okay. Now, let us see what is the power supply requirement, what is the maximum or we should say what is the minimum value of VEE one requires for this circuit to operate. Okay. Now, so here you have a current source, let us see, you have a current source, this resistance, okay, the drop across these resistances, okay, is one drop. So, let us call this V R across the resistance for the current source. Okay. Then you have the VCE of this transistor. Okay, this is VCE. All right. Then what you have the VBE of this transistor. Okay. From here this is VRCS, then you have VCE. Okay. From here to here you have VBE, another VBE. Okay. I think another VBE will be there. Okay. I'll just remove this now. All right. So, this is VBE, and then from this point to this input point here you have another VBE. Okay. So, this is another VBE. All right, and the maximum, so this value, okay, this must be at least minus VBE here. Okay. So, there is another VBE again here, all right, at the base. Okay. All right, here it is minus VBE to minus VBE minus 500. So, there should be at least another VBE here. Okay. So, the totally you have how much? VBE, 3 VBE plus VCE plus VRCS. Okay. So, VEE minimum is equal to 3 VBE plus VCE VRCS. Okay. All right. Now, for these circuits, okay, VBE is actually given by, VBE we can write is VBE intrinsic, that is the intrinsic drop across the PN junction, plus IB RB plus IE RE. Okay. All right. Now, so these are the drops across the parasitic resistances. Okay. Now, for a small size device, okay, the resistances are usually large, because the resistance depends on the cross sectional area. Okay. If you have a smaller size device, you have a larger resistance. Okay. So, if you talk of very high speed devices, okay, the extrinsic resistances are quite large. Okay. And so, this value VBE may be as large as 0.9 volts. Okay. It is not that the 0.9 volts is dropped across the PN junction, but a large part is dropped across the parasitic base and emitter resistances. Okay. So, say VBE is 0.9 volts, VCE, so this transistor, suppose we assume it is 0.5 volts, okay, the collector emitter drop, and VRCS is 0.2 volts, say, then we have 3 into 0.9 plus 0.5 plus 0.2. So, which means how much? 2.7, 3.2, 3.4 volts. So, this is actually the modulus of that. So, VEE we can have is minus 3.4 volts. Okay, for this structure, and the current of course, the I, or I should say I write it here, I is equal to ICS, the current source value flowing through the current source. Okay, there is one current source here. Okay, plus there are 4 levels, there are 2 level shifting, okay, parts. Okay, the current will flow through these two. Okay, one current source, 2 level shifting, and 2 emitter followers. Okay, so you have ICS plus 2 I should say level shifting circuits plus 2 I emitter followers. So, this is the amount of current which flows. Okay, and you have the voltage, and so the voltage into current is the power dissipation. All right. So, now if you have to reduce the power dissipation, what you have to do is you have to reduce the you have to tackle it both ways, that is you can reduce the voltage, power supply voltage, as well as the current. Okay. So, a circuit which has a lower power dissipation can be constructed by making a small modifications in this circuit. Okay. Firstly, what you can do is you can remove this emitter follower stages. Okay. So, basically what you have now is this goes in directly here as the thing, and here goes in directly here. Okay. So, you have removed the emitter follower. Okay. All right, the emitter follower has been removed, okay, which means what? That basically the output voltage is no longer varying from minus VB to minus VB minus 500 volts, but the output voltage. So, here this is Q bar and this is Q here. Okay. The output voltage variation now is from 0 to minus 500 millivolts, and VR would be centered somewhere is equal to minus 250 millivolts. Okay. All right. So, the input voltage here is no longer, okay, at the clock input here is no longer minus VB minus 500 volts, but it is now from 0 to minus 500 millivolts. Okay. So, what is happening? What has happened now? What is the change in the VE minimum? So, basically what we have done is we have increased the input voltage by VBE, all right. It was initially the previous circuit minus VBE to minus VB minus 500. So, we have raised the input voltage by VB, shifted it up. The VR also has been shifted up by VBE. Okay. So, there is no problem, okay, as such. Of course, you may have to be careful about the fan out, as we had discussed in the first class, but there is always a trade off. Okay. So, here we are looking at low power dissipation. Okay. So, what happens to VE min? Since the input voltage now has been shifted by VBE, okay, so the input voltage can be straight away 0 volts. Okay. So, there is no extra drop of VBE here. All right. So, the VE minimum is going to be, instead of the previous case we had 3 VBE plus VC plus VRCS. So, in this case it is going to be 2 VBE. All right. 1 VBE is less. Okay. So, the VE min for this circuit is equal to minus 2.5 volts, okay, and the I has again also been reduced. Okay. What happens that the emitter followers have been removed. Okay. So, you have 2 ILS, 2 level shifting plus ICS. Okay. So, this is a low power circuit. Okay. All right. Now, okay. Now, what we shall do is, so this is about the low power stacked ECL circuit, okay, to achieve a D flip flop. Okay. Now, I will come to the newer concept, okay, of the circuitry, okay, which is called the new circuit which has been proposed. So, the circuit is called by the name CMCL, okay, or current mode control logic, okay, current mode control logic. I think, okay. Now, we shall see what is the modifications here. Okay. In this circuit, it is slightly different, it looks different. Okay. What we have here is a current, sorry, I made a mistake, this current mirror control logic, sorry, current mirror control logic. So, what you have here is a current mirror arrangement. Okay. Here you have a current, I suppose you are aware of what is a current mirror. Okay. That is basically you have a circuit here, okay, which controls the current flowing in some other circuit. Okay. So, what you have is here okay. Now, here this goes in here and this goes in here as the input. Okay. So, this all this remains the same as in the previous circuit. This is D, this is VR. Okay. And again, what you have here is the input voltage variation is from 0 to minus 500 millivolts. So, this is 0, this is minus 500 millivolts. Okay. All right. Now, what you have here is, you see, this is the current mirror arrangement. Okay. This transistor and this transistor, okay, and this is another current mirror arrangement. So, basically what you have is a diode configuration here, the collector and base is shorted, okay, and whatever is the current flowing here. So, if this transistor is on, okay, so this voltage here is going to be high, all right, and which would mean that this transistor VBE will be high, okay, and this is going to be on, okay, whereas if this voltage at this node, okay, if we call it a node N1, this node N2, okay, if the voltage at node N2 is high, okay, then the base voltage of this transistor, okay, to which it is connected is going to be high, okay, and this is going to be turned on. So, basically what we want to say is, previously in the previous circuit you had an emitter coupled system here, okay, to which you are feeding the clock and clock bar, okay, and depending on whether the clock is high or clock bar is high, the left this in the upper stack, either the left part was being on or the right part, the right hand side stack emitter coupled structure was on. Okay. Here, instead of having an emitter coupled structure here at the lower part of the stack, okay, you have an arrangement like this. Okay. So, basically what is going to happen is, say if clock is high, okay, that means here the voltage is 0 volts, say, okay, that would mean that clock bar is low, okay, that is minus 500 millivolts, okay, and then which would mean that voltage at node N1 is going to be high, because it is basically a level shifting here, okay, voltage at node N1 is going to be high and the voltage at node N2 is going to be low, okay. So, which means that between these two transistors, say transistors T1 and T2, okay, T1 would be having a much larger current compared to T2, okay, T1 and T2, T1 is drawing much larger current compared to T2, because the base voltage of T1, which is the same as the node voltage N1, okay, is much higher than the base voltage of T2, okay. and that is how basically transistors T3 or T4 can be on, okay, whereas T5 and T6 will be off because T2 is carrying very little current. Okay. So, T5 and T6 will remain off, T3 and T4 will be on. Okay. Now, in this case, what is the maximum value of the power supply voltage? What you have here is this again VRCS, okay. Let us say this is the voltage, okay. From here to here you have VBE, okay, at the base at node N1, and from here you have another VBE. All right. So, what is the maximum value of the input voltage? What is the maximum value of the power supply voltage? It is twice VBE plus VRCS, okay, which means it is just 2 millivolts, 2 volts. Twice VRCS, twice VBE is 1.8 volts and VRCS is 0.2 volts. So, the maximum, the power supply voltage can be as low as 2 volts, okay, all right. So, here this is going to be VE min is going to be twice VBE plus VRCS, okay, which means it is as low as 2 volts, okay. And also the current, of course, it is the sum of, see, what we want to say is that one of these is going to be on at a time, as well as one of the this is going to be on at a time. So, we can say it is ILS, I is equal to ILS plus ICS. Basically, you see, let us see, if it is 2 volts, let us say that minus VE is minus 2 volts here, okay, and the input voltage is clock and clock bar 0 and minus 500 millivolts, okay. So, if it is 0, the node 1 N1, if we assume VB is 0.9 volts, N1 is going to be 1.1 volts, okay, whereas N2 is going to be minus 1.4 volts, isn't it, minus 0.5 at the clock bar input, minus, see basically what you have is 1.5 volts is going to be dropped between this VBE of this level shifting transistor plus this diode arrangement here, okay. So, the maximum voltage which can be dropped if both of them are carrying the same current per junction is 0.75 volts, okay. So, this transistor, okay, is going to be off, okay, which is less than the requirement of VBE, which we have said is 0.9 volts, okay. So, if this is say 0.75 volts, okay, so if we say that at the base of T2 you have 0.75 volts and at the base of T1 you have 0.9 volts, okay. So, VBE1, so if you say that VBE1 is equal to 0.9 volts and VBE2 is 0.75 volts, okay, then you can say that the two currents, so ICS1 by ICS2 will be equal to, that is the two current source values, okay, is equal to exponential, because it is dependent on exponential VBE. So, it is going to be exponential 0.9 minus 0.75 by VT. So, this is around 320, okay. So, the current flowing through one branch here is going to be about 300 times that of the other branch. So, we can safely say that only the current is actually flowing in one of them and the other current is almost 0, okay. That is basically depending on which node N1 or N2 is high, okay, one of the branches are going to control the current, okay. So, here with a current mirror, okay, instead of an emitter coupled structure, okay, we choose which branch is going to be conducting, all right. So, and in the process what happens is the power dissipation is reduced because of the fact we require a lower power supply voltage. At the same time, the current requirement is also less. Okay. In fact, in that paper, okay, they have given some results. Okay. They have fabricated D flip flops operating at, I think D flip flops, just give you some results at 3 gigahertz clock frequencies, okay, and drawing power at 1.8 milliwatts per flip flop. Okay. So, that is the level of power, only 1.8 milliwatt per flip flop, okay, and also they have done fabricated T flip flops at operating at 4.3 gigahertz, and they claim that this is the lowest power dissipation for any gigahertz family. Okay. All right. And I will also give you the references. So, if you are interested, you can go through it. K. Kishine and others, IEEE Journal of Solid State Circuits, volume 32, number 2, pages 215 to 221, February 1997. Okay. So, this is a new logic family, I mean a sort of variation of the ECL, where you achieve a lot of reduction in power dissipation, which is the stumbling block in ECL. Okay. And with this advancement, one hopes one can really realize LSI level circuits using ECL. Okay. That is what they claim in that paper. Okay. All right. So, in fact, this is a D flip flop. Using the same concept here, one can actually realize other logic circuits also, okay, just like a stack, okay, just like a 2-level stack. Okay. You can realize other logic circuits where the lower level is actually controlled not by an emitter coupled structure, but by a current mirror arrangement, okay, as given here. Okay. So, I will just give an example. I will just quickly, maybe I will just modify this. Okay. It is easy for me to do on the blackboard. Okay. Okay. If I want an exclusive OR circuit, okay, just like a D flip flop we have discussed, you know, what does a D flip flop do? Okay, just the difference between D flip flop and exclusive OR. Okay. D flip flop, it is the Boolean function is Qn is equal to clock into Qn minus 1 plus clock into D plus clock bar into Qn minus 1. Here in an exclusive OR it is A bar B plus A B bar. Okay. So, it is quite similar, that is what you have to do is here in one of the inputs you put A and here you put A bar. Okay. So, if A is high, one of these nodes will go high, and A bar, the other node is going to go high. So, if A is high, then this circuit is on, if A is low, then the other circuit is on. Okay. So, what you do is here, okay, what you have to do is you put a reference voltage here, okay. So, here this is the reference voltage, sorry, this is the reference voltage, okay, and the other input, okay, here you put B, okay, and here also you put B, here also you put B. Okay. So, what you have to do is if A is high, that is here in this circuit, okay, this output is equal to B bar. Okay, you have B here. So, this is reference voltage. So, this corresponds just like an ECL gate, this corresponds to B bar NOR output, B bar this corresponds to B. Okay. So, exclusive OR, just F is equal to A B bar plus A bar B. So, when A is high, F is B bar, when A is low, F is B. So, when A is high, that is, this is on, this part is on, okay, this is B bar, all right, and when A is low, then this circuit is on, the output should be B. Okay. So, where do you get it? This is B, you get here B, isn't it? So, you should short these two outputs here, and this is going to be F A exclusive OR B. Okay. The other two outputs, okay, gives the complement actually. All right, it is clear. So, if A is high, this part of the circuit is on, so this is going to be A exclusive OR B. Okay, if A is high, F is going to be B bar. If A is low, okay, then this gives B. Okay, so the output is going to be B. All right, so these two are shorted. Okay, so that gives A exclusive OR B. The other two outputs is these two other collectors can be shorted to give exclusive NOR combination. So today we have discussed a new circuit concept, okay, that is the current mirror control logic, okay, and this is again a variation of ECL gate, okay, and it helps in reducing the actual power dissipation in ECL gates, okay, ECL family of logic gates. So there has been a lot of work in this area, and this gives you some idea of the ongoing work which is going on. Okay, a lot of people are still working at it, how to reduce the power dissipation. Next few classes we shall look at the attempts to increase the speed of ECL gates still further. Okay, the ECL is the highest fastest logic family, but there is a continuous need to achieve higher and higher speeds. Okay, so what is the way people have done it, okay, from technology point of view as well as maybe from the circuit point of view. Okay, so